Let's explore the standard equation of a circle on a coordinate plane. This equation will let us precisely define any circle using just its center point and radius. Every circle has a center point. We'll denote its coordinates as h, k, where h is the x-coordinate and k is the y-coordinate of the center. The radius, which we'll call r, is a fixed distance from the center to any point on the circle. This constant distance is what defines a circle geometrically. A circle is defined as the collection of all points in a plane that are exactly radius r away from the center. This equal distance property is what gives a circle its perfect round shape. Let's consider any arbitrary point on our circle, which we'll label as x, y. This represents any of the infinitely many points that make up the circle's circumference. By definition, the distance from our center point h, k to any point x, y on the circle must equal exactly r. This key constraint is what we'll use to derive the circle's equation. To express this distance constraint mathematically, we use the distance formula derived from the Pythagorean theorem. The square of the distance between 2 points equals the sum of squares of differences in their coordinates. This gives us the left side of our equation, open parentheses x minus h, closed parentheses squared, plus open parentheses y minus k, closed parentheses squared. The h and k in our equation represent the x and y coordinates of the center point. We subtract these values from x and y to calculate the horizontal and vertical distances from any point to the center. The x and y variables represent the coordinates of any point on the circle. For a point to be exactly on the circle, its coordinates must satisfy our equation. Since the distance from the center to any point on the circle equals r, and we've expressed the square of this distance on the left side, the right side of our equation must equal r squared. The Pythagorean distance formula connects the left and right sides perfectly. So our complete equation is open parentheses x minus h, closed parentheses squared, plus open parentheses y minus k, closed parentheses squared, equals r squared. This elegant formula is the standard equation of a circle, expressing the fundamental property that all points on the circle are equidistant from the center. This equation completely defines our circle. Any point whose coordinates make this equation true lies exactly on the circle, and any point that doesn't satisfy the equation lies either inside or outside the circle. For our specific circle with center at 1, 2 and radius 2.5, we can substitute these values into the general equation. This gives us open parentheses x minus 1, closed parentheses squared, plus open parentheses y minus 2, closed parentheses squared, equals 2.5 squared, or 6.25. Let's verify this with another point on our circle. If we take any point on the circumference and plug its coordinates into our equation, the result will always equal r squared. The beauty of this equation is that it works for any point on the circle. Whether we move clockwise, counterclockwise, or jump to any position on the circumference, the distance to the center remains constant at exactly r units. The standard form open parentheses x minus h, closed parentheses squared, plus open parentheses y minus k, closed parentheses squared, equals r squared gives us a powerful tool to analyze, create, and work with circles in the coordinate plane. This equation directly encodes the definition of a circle as all points equidistant from a center. Let's explore the standard form equation of a circle, which is written as open parentheses x minus h, closed parentheses squared, plus open parentheses y minus k, closed parentheses squared, equals r squared. In this example, we have a circle centered at the origin, where both h and k equal 0. The radius of our circle is 2 units, which determines how far the circle extends from its center point. Now let's examine what the h parameter represents in our equation. The h value determines the horizontal position of the circle's center point. When h is positive, the center shifts to the right, and when h is negative, it shifts to the left. Watch what happens as we increase h from 0 to 2. The entire circle shifts 2 units to the right along the x-axis. This happens because we're subtracting h from x in our equation, so a larger h value moves the circle in the positive x direction. Next, let's look at the k parameter, which controls the vertical position of the circle's center point. Similar to h, when k is positive, the center shifts upward, and when k is negative, it shifts downward. As we increase k from 0 to 1, notice how the circle moves 1 unit upward along the y-axis. Our circle is now centered at the coordinate point 2, 1. Again, this happens because in our equation, we're subtracting k from y, so increasing k shifts the circle upward. To isolate the effect of the radius parameter, let's reset both h and k to 0, which places our circle back at the origin. This will help us clearly see how the radius affects the circle's shape. Finally, let's examine the r parameter, which represents the radius of our circle. The radius determines the size of the circle. Specifically, it's the distance from the center to any point on the circle's edge. As we increase the radius from 2 to 3, the circle expands outward in all directions. The squared term in our equation ensures that the distance from any point on the circle to its center is exactly r units, creating a perfect circle with radius 3. These three parameters completely define a circle in the Cartesian coordinate system. By adjusting h, k, and r, we can position and size any circle we want on the coordinate plane. To summarize what we've learned, h controls the horizontal position of the center, k controls the vertical position of the center, and r determines the size or radius of the circle. Together, these parameters give us complete control over our circle's placement and dimensions. Let's explore the equation of a circle when it's centered at the origin of our coordinate system, which is the point 0, 0. This special case gives us a simpler form of the circle equation. The standard equation of a circle is written as x minus h squared plus y minus k squared equals r squared. In this equation, the point hk represents the coordinates of the circle's center, and r represents the radius of the circle. When a circle is centered at the origin, both h and k equal 0, since the origin has coordinates 0, 0. Let's highlight these parameters in our equation. Now, let's substitute h equals 0 and k equals 0 into our equation to represent a circle centered at the origin. When we simplify x minus 0 squared plus y minus 0 squared, we get x squared plus y squared equals r squared. This is a much cleaner equation and is the special form that applies only to circles centered at the origin. Let's mark the origin point with this yellow dot. This is the center of our circle. In our coordinate plane, this point has both x and y coordinates equal to 0. I'll move our simplified equation to the corner so we can refer to it as we explore how different radius values affect our circle. Remember, in the equation x squared plus y squared equals r squared, only the radius r will change while the center remains fixed at the origin. Let's begin with a radius of 1. This gives us the equation x squared plus y squared equals 1 squared, which simplifies to x squared plus y squared equals 1. Here's our circle with radius 1 centered at the origin. Notice how every point on this circle is exactly 1 unit away from the center. You can verify this for points like 1, 0, 0, 1, negative 1, 0, and 0, negative 1, which all satisfy our equation. Now let's increase the radius to 2. Our equation becomes x squared plus y squared equals 2 squared, or x squared plus y squared equals 4. Watch how the circle expands to include all points that are exactly 2 units away from the origin. Let's continue by increasing the radius to 3. Now our equation is x squared plus y squared equals 3 squared, which is x squared plus y squared equals 9. Notice how the circle grows larger while maintaining its center at the origin. Points like 3, 0, 0, 3, and others that are exactly 3 units from the center now lie on our circle. Finally, let's set the radius to 4. Our equation becomes x squared plus y squared equals 4 squared, or x squared plus y squared equals 16. The circle continues to grow, encompassing all points that are exactly 4 units away from the origin. As we've seen, when the radius increases, the circle expands uniformly in all directions from the center point. In our equation x squared plus y squared equals r squared, only the right side changes as r changes. The relationship between all points on the circle and the center remains the same. They're always exactly r units away. This simple form of the circle equation is why circles centered at the origin are particularly easy to work with. Any point xy that makes the equation x squared plus y squared equals r squared true will lie exactly on the circle, and all such points are exactly r units away from the origin. To summarize, when a circle is centered at the origin, its equation simplifies beautifully to x squared plus y squared equals r squared. This equation directly embodies the definition of a circle, all points that are exactly r units away from the center. Let's explore how to derive the equation of a circle with a center at the point 2, -3, and a radius of 5 units. We'll use the coordinate plane to visualize this circle and develop its equation step by step. This red dot represents the center of our circle at the coordinates 2, -3. To find the equation of this circle, we need to recall the standard form of a circle equation. The standard form of a circle equation is x minus h squared plus y minus k squared equals r squared. This equation expresses the fundamental property of a circle. All points on the circle are exactly the same distance from its center. In this equation, h and k are the x and y coordinates of the center point, highlighted in green. The variable r, highlighted in blue, represents the radius of the circle. The squared terms ensure we're working with positive distances as we're applying the Pythagorean theorem. To derive our specific circle equation, we'll substitute the known values one by one. First, since our center is at x equals 2, we substitute h equals 2 into the equation. This gives us x minus 2 squared for the first term. Now we need to substitute k equals -3, since that's the y-coordinate of our center. This gives us y minus -3 squared for the second term. When we have y minus -3, we can simplify this expression. Subtracting a negative number is the same as adding the positive number, so y minus -3 becomes y plus 3. Finally, we need to substitute the value of r squared. Since our radius is 5, we know that r squared equals 5 squared, which is 25. This completes our equation. X minus 2 squared plus y plus 3 squared equals 25. Let's now visualize what this equation represents. We'll draw a circle with center at the point 2, -3, and radius 5 on our coordinate plane. Every point on this blue circle satisfies our equation. They are all exactly 5 units away from the center point. Here's one radius of our circle, drawn in yellow. The distance from the center to any point on the circle is exactly 5 units. This is the geometric meaning behind our equation. It's the set of all points that are exactly 5 units away from the point 2, -3. Our final equation is x minus 2 squared plus y plus 3 squared equals 25. This is called the standard form of the circle equation because we've expressed it in terms of the center coordinates and the radius. If we had different values for the center or radius, we would follow the same process. Substitute the center coordinates for h and k and the squared radius for r squared. This method works for any circle in a coordinate plane. Let's explore how the equation of a circle changes when we move its center from one point to another on the coordinate plane. When a circle is centered at the origin of the coordinate system, its equation takes the simplest form, x squared plus y squared equals r squared, where r represents the radius of the circle. Here we have the equation x squared plus y squared equals 16. This represents a circle centered at the origin, point 0, 0, with a radius of 4. We can verify this because the radius squared is 16 and the square root of 16 is 4. When we move a circle away from the origin, we need to adjust its equation to account for the new center coordinates. The standard form becomes more complex as we need to track the horizontal and vertical displacement. Let's transform our blue circle into a new circle with center at the point 2, -3, and radius 5. Notice how this will require changing both the position terms in our equation and the constant term, which represents the radius squared. Watch carefully as the circle gradually shifts position and changes size. I'll simultaneously transform the equation to match each stage of this metamorphosis. This shows how the mathematical formula directly relates to the geometric properties of the circle. As the center moves from the origin toward the point, 2, -3, notice how the terms in the equation change. We're now subtracting 0.5 from x and adding 0.75 to y, which reflects the new center coordinates. The radius is also increasing, making the constant term larger. Continuing the transformation, our circle's center is now at 1, -1.5. In the equation, we're subtracting 1 from x and adding 1.5 to y. The radius has increased to approximately 4.5, making the right side of our equation 19, which is 4.5 squared. The circle continues to shift toward our target position. The center is now at 1.5, -2.25, and the radius is about 4.75. This is reflected in our equation where we subtract 1.5 from x and add 2.25 to y, with the constant term becoming 22. Finally, we reach our destination. The circle is now centered at the point 2, -3, with a radius of exactly 5. Our equation has transformed to match open parentheses x minus 2 close parentheses squared plus open parentheses y plus 3 close parentheses squared equals 25. Let's examine our new circle. It's centered at the point 2, -3 and has a radius of 5. Note that in the equation, we subtract the x-coordinate of the center, which is 2, from x. For the y-coordinate, since it's -3, subtracting it is equivalent to adding +3, which is what we see in the equation. Pay special attention to how the center coordinates appear in the equation. The x-coordinate 2 is subtracted from x, and the y-coordinate -3 leads to adding 3 to y. This pattern is crucial for understanding how to write the equation of any circle given its center and radius. The general form of a circle's equation is open parentheses x minus h, close parentheses squared, plus open parentheses y, minus k, close parentheses squared, equals r squared. Here h and k represent the center coordinates, hk, and r is the radius. Remember that if k is negative, then y minus k becomes y plus the absolute value of k. For our red circle, h equals 2, k equals -3, and r equals 5. When we substitute these values into the general form, we get exactly the equation we derived. Open parentheses x minus 2, close parentheses squared, plus open parentheses y, minus -3, close parentheses squared, equals 5 squared, which simplifies to open parentheses x minus 2, close parentheses squared, plus open parentheses y, plus 3, close parentheses squared, equals 25. The key insight here is that the equation of a circle directly encodes its geometric properties. A circle centered at the origin has the simple form x squared plus y squared equals r squared, while moving the center to any point, hk, requires adjustments to the equation using the pattern we've observed. Let's explore the key concepts of circle equations, which allow us to mathematically define any circle in the coordinate plane. The standard form of a circle equation is shown here. It's written as x minus h squared plus y minus k squared equals r squared. In this equation, we have 3 key parameters. The coordinates h and k, highlighted in blue, represent the center point of the circle. The value r, highlighted in green, represents the radius of the circle. Let's examine each parameter more closely. The value h represents the x-coordinate of the circle's center. The value k represents the y-coordinate of the circle's center. And r represents the radius of the circle, which is the constant distance from any point on the circle to its center. Now, let's understand where this equation comes from. The circle equation is actually derived directly from the distance formula in coordinate geometry. The distance between any 2 points in a coordinate plane is given by the square root of the sum of squares of the differences in their coordinates. For a circle, every point on its circumference is exactly the same distance from the center, that distance being the radius. Armed with this understanding, let's apply our knowledge to analyze a specific circle equation. Here's our example equation, x plus 1 squared plus y minus 4 squared equals 16. Our task is to identify the center and radius of this circle. To identify the parameters, we need to rewrite the equation in standard form. Notice that x plus 1 can be rewritten as x minus negative 1, so our equation becomes x minus negative 1 squared plus y minus 4 squared equals 4 squared, since 16 equals 4 squared. By comparing with the standard form, we can now identify our parameters. The value of h is negative 1, meaning the x-coordinate of our center is negative 1. The value of k is 4, meaning the y-coordinate of our center is 4, and the radius r is 4 units. Let's visualize this circle on a coordinate plane to get a better understanding of what it looks like geometrically. Here's our coordinate plane, where we can visualize the circle. Each grid unit represents 1 unit in both x and y directions. First, let's plot the center of our circle at the point negative 1, 4. This is the point hk that we identified from our equation. From this center point, the radius extends 4 units in any direction. Here I'm showing a vertical radius extending upward, but remember that the radius is the same length in any direction from the center. Now we can draw the complete circle. Every point on this yellow curve is exactly 4 units away from the center at negative 1, 4. This is the geometric representation of our equation x plus 1 squared plus y minus 4 squared equals 16. As we can see, the circle equation provides us with all the information we need to uniquely determine a circle in the coordinate plane. By identifying the center coordinates and radius from the equation, we can visualize and work with circles in analytical geometry.